Hey, Dawson is with us. And I wonder who else is with us. Let me see. Mohammed, Nicholas, Dawson, Bryce, Reagan, Alex. Nathan. I don't know if I called everybody, but we got a pretty good crowd, pretty good class there. This is the 12th of November. And your test, I think, is made available to you. It's due Sunday. It should be available today. Exam 3 should be available now, I believe.
Available yet?
Is it available now?
No, it's not. I checked it. It's not there.
Okay. I'll check on it. And if I have to, I'll notify my IT person.
Thank you. Also, Mr. Griffin, can you go over the problems 7-92 and 134E?
Well, yeah, let me see what I can do here, Mohammed. I need to talk to you about device efficiency for sure. And I think this is due Sunday, right? Let me see. Yeah, it's due Sunday. But Mohammed says it's not available right now. Should be. Let me. Hey, can you check again, Mohammed? Check. Was that
It's
Mohammed?
not available because I was just looking for it too. It's not on there.
Okay, well, let me call my IT person. Hang on. We'll see if I can get my IT person here. I've got my own IT person. She lives here. It's my daughter. She's 30. And she's pretty good with computers. We'll see if I can get her. Let's do Sunday. And it's on chapters 5, 6, 7.
Your call has been forwarded to an automatic voice message system. 91870698113 is not available. At the tone, please record your message. When you have finished recording, you may hang up or press 1 for more options.
Hey, Rebecca, my wonderful students informed me that this thermo exam is not available. I thought it was going to be available this morning. Can you please check on that if you have time? Or I can later. Thanks for everything. Talk to you later. Ta-ta. Okay, now how do I get out of here? I guess I just push that button. There we go. Okay, well, we'll take care of it. We got till Sunday night at midnight. It'll be fine. Now, Mohammed had wanted me to do something. Say it again, Mohammed. What did you want?
Want to do you to 729 and 134E?
Okay, well, let me find that. 729.
No, it's 92, not 29.
Oh, 792.
Sorry.
Yeah, we could do that one. What was the other one?
134E.
134E. Okay. 34E. I want to do the 792 for you, Mohammed. We studied the specific entropy generation last time. Review your video,
Yeah, on the 134E, I just want you to draw the TS diagram, not the whole thing. I'm just wanting you to draw the TS diagram, not the whole
I
thing.
ran into a little bit of difficulty with that problem as well. This is
the
Alex.
134E.
Yeah.
Who am I talking to?
This is Alex.
Alex, what was the difficulty you ran into, Alex?
I drew out both the TS and the PV diagram, but I
Yeah.
had some problems getting the numbers from the book that were like correct. That's where I ran into some problems. Because overall, the problem's not too difficult. It just comes down to pulling the right number out of the book.
Right. And that was at 134E, is that what you said?
Correct.
Okay, well, 134E, I believe, is a throttle. And I can give you some tips about it. Let's talk about that. And then we can talk about that other one that Mohammed wanted. On this one here, if you do a PV diagram, is that my calculator going beep, 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 beep? I don't know. You'll discover if you do this, that you're in what they call compressed liquid. Alex, did you discover you were in compressed liquid?
Yes, I got that far.
Good for you. And I think you started off at 90 Fahrenheit. Well, see, 90 Fahrenheit comes down here and it does a thing like that. But see, we're there at, call it state one. We're in this compressed liquid. And here's what you need to know, Alex. The specific volume at state one is equal to the V sub F. That's the saturated vapor. See, this line here is called saturated vapor. No, I'm sorry. Saturated liquid. And that VF is the specific volume at saturated liquid. For saturated liquid, I can't say saturated. Why am I talking like Elmer Fudd? Saturated liquid. There we go. Wascally Wabbit. You guys don't know what I'm talking about. You've never watched Bugs Bunny cartoons, have you? If anybody's ever watched it,
Looney Tunes.
oh, you have. You have watched Bugs Bunny. Okay, good. Well, anyway, right. Now you look it up for 90 degrees and you'll find it. Oh, here's my IT person. Hang on just one tiny minute. Hi, Rebecca. You're in class? Oh, thanks for asking. It's the thermodynamics class. They can't seem to pull up their exam, and it should be available this morning. Well, while she's working on that, let me tell you this. The specific entropy at state one is equal, let's use a little s, there we go, is equal to the little SF. What that is the saturated liquid specific entropy at 90 degrees Fahrenheit. That should help you, Alex. Does that help you any?
Yeah, so I got those values. I got H, S, and the specific volume, and I was kind of confused where to go from there. Because I know to get the specific entropy generation, it's just a change in entropies, right?
It turns out that way, yeah.
And so we have to get, from this, we get S1, but I had some difficulty getting S2. Or I guess
Okay, now
the final S.
here's how you do it, Alex. This is a throttle. And you really need little h1. Well, little h1, you can use little hf for the saturated liquid at 90 degrees, just like these others. And the beauty is when you have a throttle, h1 is going to equal h2. Now what this thing does is it has a irreversible process, and it goes to 10 degrees Fahrenheit. Here, I'll draw it for you. There's your 10 degrees Fahrenheit. There's your state 2. And see, if you got H1, which I showed you how to get, it's going to equal H2 because this is the first law for throttles. And once you got H2, yeah, hey, let me turn up your volume. Say it again, please. Oh, okay, I will. I'll take you off speaker. I think you're off speakerphone now.
Okay, I know chorus is the first part, but what are the numbers after chorus
Oh,
in your password?
it's well, it's 10398 is the.
No, your password, Dad, is chorus and the number.
Oh yeah, it's 1898.
Okay, and your CCID is
1039843. Yeah. It's Horace, HORACE. You have to go capital H.
Yeah, I have that.
1898. Number sign. Did you do the number sign?
Yeah, it's not working. You haven't changed it?
I don't think so. Should work.
Okay, I got it. And which class did you say?
It's the thermo class. It's exam 3, and they said it's not available. It should be. Let me go ahead and I'll teach them what to do here, but I'm listening to you. Okay, guys, let me show you one last thing here. See, this is inside the vapor dome. So what you do is you go HF plus X2 HFG. And these you can look up now because they're at 10 degrees Fahrenheit. And you can solve for X2, the quality at state 2. Now, once you get that, you can find little S2 because it's going to equal little SF plus the quality at 2 times little SFG.
Yep,
And
that was the missing piece.
That's the missing piece.
That was the missing piece.
To the jigsaw puzzle, and you can do it now. Is everybody happy with 7134, and can I move on? Because I want to do that.
It should be available now.
Hey, the IT person says that test should be available now. I just got word from the IT person. Hey, thanks a lot. I'm sure that's fine now.
All right.
I'll talk to you later, Tata.
It's still not showing up.
It's not showing up?
I
No,
got it.
you got it?
Oh,
Yeah.
I heard we got it. Well, Shazam, how about that? So we're back in business, do you think? Okay, that was fun. Now let's do this. I think it was 792. Isn't that what my friend said?
Yes, sir. 792.
Yeah, okay, well, let's do it. What the heck? Let's do it. Let me make some room. But that exam is chapters 5, 6, and 7. And I'm sure you'll do just fine on it. And I'd really appreciate it if you'd write nice and thick and big and have your lights on in your room. I get some papers and I'm straining my eyes to try to read what you guys have sent me. I don't know. I think you need more light maybe, or get a darker pencil or something. Help me out here. My eyes aren't what they used to be. Okay, now we're looking at 792. And the topic is the efficiency. Here we go. Look at da 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 da. It's efficiency. That's what we want. Of turbines. The efficiency of turbines. Yeah. Okay. Well, now here's how you do this. Wait a minute. I just got a little ding 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 ding. This thing's going to drive me crazy. I don't know what that is. Somebody wanting money, probably. Yeah, like I got lots of that. Okay, you know the drill. You're going to draw a turbine schematic here. And this is steam, so you can put H2O right there. That'll work. And coming in, you have 1800. Let me write this stuff down. 1800 kilopascal, 400 Celsius. And the exit is 200 kilopascal. 150 Celsius. What's the efficiency? I wish they wouldn't use that word isentropic, because that gives students the impression that this is reversible and adiabatic, and it's not. We're going to examine what would happen if you did have an isentropic turbine, but this turbine is an irreversible process. It is not an isentropic process. But the equation for the efficiency of a turbine goes like this. It's a Greek letter eta with a little t on there. And you take your actual work per mass and you divide by the work per mass if the turbine was a reversible process, and you'll always get less than 100%. Maybe you'll get 90% or 80 or 70% or something like that. But that's the equation. Now what do we do now? Well, we need to draw our PV and TS diagrams, don't we? Well, let's do that. Here goes. And I need some room here. How about do I have room down here? Let me look. Yeah, I think I do. Okay, we'll do a PV down here. There's your vapor dome. Now, 400 Celsius, you know what? That's hotter than the top of the dome. the top of the dome is 374. So what we're talking about is an isotherm, 400 degrees Celsius like that, and 1800 kilopascals. Well, I don't know, that's in here someplace. We'll just fake it and say 1800 kilopascals and come over here and bingo, there's your state one. You're coming in at state one now. And we're going to a lower pressure, quite a bit lower, 200. You know what? 200 is a lot lower than 1800 kilopascals. And you know what? 150 is a lot lower too. 150 is colder than 400. So somewhere in here is 150. We'll try to draw it here somehow. I'm just curious what the saturation pressure is for 150. Let me go to my table and find the table here. Hang on. I'm looking for water at 150 Celsius. And it says 475 kilopascals. So here, let me make this just a little lower, maybe. Here's your 150. And that pressure right there happens to be 475. 475.9 kilopascals. I'm on table B.1.1. And that temperature there is 150 degrees Celsius. And your process is going to go like this. It's a dashed line. It's a dashed line, and you're going down to 200 kilopascals. Well, see, 200 is right about here someplace. 200 kilopascals. Does that show up? Yeah, kind of. There's state two. Now, I'm going to ask one of my excellent students something here. I'm going to ask my friend Reagan. Unmute and say hello, Reagan, please.
Hello.
Reagan, I got a dashed line here. When I make a dashed line, that's a special kind of process. Do you know what that represents when you make your process with a dashed line, Reagan? What does it mean?
I think that's is a topic.
I'm sorry, say again, please.
Is a topic. Isotopic.
No, it's not. If it was isentropic, it would be a solid, it'd be a solid line. No, it's a dashed line. Let me ask somebody else. Well, but that was an intelligent answer, but it was wrong. Sometimes intelligent answers are wrong. Nicholas, Nicholas Sabrata, unmute and say hello. Yeah, hello. Nicholas, what is the dashed line process? What is that?
Is it adiabatic?
No, you lost on that one, Nicholas. I'm going to try somebody else. Nice guess, though. It was intelligent. That was intelligent. Let's go to Nathan. Nathan, unmute and say hello, Nathan.
Hello, is it irreversible or?
That's it. That's it. This is the irreversible, or you could say actual. See, actual processes are irreversible. Like, I'll give you an example. Go to your refrigerator and get an egg. and then drop it on the kitchen floor. And what happens is the shell cracks and the yolk splits and the white of the egg just kind of scoots around on your kitchen floor. That process is irreversible. You're not going to get that egg back inside the shell the way it was. That's what an irreversible process is. And they're dashed when we do them. Okay? Did that make sense to anybody? I'm hoping. All right. Good going. All right, now we're going to find the work per mass of the actual process. Now, to do that, we have to use the first law. So let me write it. Here goes first law. First law of thermodynamics. You know how it goes. It goes, you got this memorized. We're going to get lazy here. I'm going to throw out a lot of terms. Now this is going to be 0 because this is a steady state turbine. It runs like that for hours. Nothing changes with time. Now, properties change with location. Look, 400 Celsius, 150 Celsius, that's a change. That's a cooling off, isn't it? But it's not changing with time. That 400 Celsius is the same this morning as this afternoon. It hasn't changed. The 150 Celsius, that's what it was this morning. That's what it was this that's what it'll be this afternoon. See, with respect to time, nothing's changing. Now, turbines we're going to assume are adiabatic. No heat transfer. Then you got your W dot. This is your mass flow rate. And what you need is H1 minus H2. Okay, well, we could look that stuff up. Here, look, help me do this. I'm going to do some algebra. Can you get to here with me? I did an algebra step there. And now what I'm going to do is I'm going to divide through by m dot. And that's going to give me little w. See, little w is big W dot divided by m dot. And so if you'll do that and divide through by m dot, then what you'll get is just H1 minus H2. If we can find these, we can find this is the actual work. Okay. Well, we can find it. Go to the tables and look up 1800 kilopascals. I'm trying to do that now. 1800 kilopascals in the tables. I found it. It's table B.1.3. I'm looking at B.1.3, and H1 is 1800, 400C. This is easy. We just write it down. It's 3250.9. H1 is 3250.9. See if you can find that on table B.1.3. Now the units are kilojoules per kilogram. Now I need H2. Okay, well H2 is 200 kilopascals. Got to look in the table for it. Having trouble finding it. 200 kilopascals. 150, so there it is. It's 2768.8 kilojoules per kilogram. I'm on table B.1.3, and I found these two, so I can get this work per mass. Let me do it. Here goes. 3250.9 minus 2768.8. Well, if I did that right, I'm getting 482.1 kilojoules per kilogram. That's the actual work per mass. Look here, we just figured out the actual work per mass. Now what are we going to do? Well, let me read the problem again and see what we're supposed to do. I kind of got lost there. We're doing 792, and it says they want the efficiency. Well, we got to find this. Now, here's how we do that. We write the first law of thermodynamics, but we write it for the reversible process. Now, if you have a reversible process, that'll be a solid line. It'll go like this. It'll go solid line. It'll come down here to the same pressure, but it'll be a little colder. I don't know if I drew that very wonderfully, but it'll be a little colder. I really need a TS diagram. It's a lot nicer. Wonder if I could fit that in. Let's do a TS diagram up here. Your exam is now available. My IT person put it online there. And we're going to draw a TS diagram on this problem. We are doing problem 792. And it's all about the efficiency of turbines. And here's our TS diagram. Now we know that we're starting off at a temperature bigger than the top of the dome. It's up here someplace. Not much bigger. 400 degrees Celsius is bigger though than 374. Isn't 374 the top of the dome? Let me look and see.
Yes.
I heard a yes. 374. Not that I don't trust you, but I just want to see it for myself. It says here, yeah, 374.1. The top of the dome is 374.1, so that's a little higher than, a little hotter than the top of the dome. And we're going to come down to 150. Well, 150 is down here someplace. There's your 150 degrees Celsius. Now the pressure at state 1 is 1800. So the way that works is you come up here and your isobars kind of go like that. This is the 1800 kilopascal isobar. They're funny. That's just how they go. And what we're going to do is we're going to go to the 150 in a what they call a irreversible process. Now it's still adiabatic. Both of these processes are going to be adiabatic because it's an adiabatic turbine, but this process is irreversible to state 2. But if you take a reversible process and it's adiabatic, they have a fancy name for that one of my students was mentioning earlier. It's called an isentropic process, and it'll come down here like this. straight down because isentropic processes, I don't know what to call this, call it state 2s maybe. Give it a name. There you have it. It's going to be at the same, it's got to have the same pressure. Now let me doctor this up just a little bit. It's got to have the same pressure. There's state 2s. And here, let me just do a little bit of fudging here to make this pretty. Sometimes when you do these diagrams, you have to kind of fudge a little bit to get them to look just right. Now this is your actual state 2, and here's your pressure. And this pressure here is 200. This is your 200 kilopascal isobar. Both of these processes are going from 1800 to 200. It's just that this one is dashed. I didn't do a very good job of dashing it, but there you have it. And it's an irreversible adiabat, whereas this one is a solid line, and it's a reversible adiabat. Well, let me refresh your memory. A reversible adiabat has a very special name, and we've mentioned it already in this class a couple of times, but I'm going to see if Julian, unmute and say hello, Julian, please.
Hello.
Julian, if you have a reversible adiabat, it's got a special name. What's the name of it? It's got a special name.
Is it isentropic?
That's it. He's got it. It's called an isentrope, or an isentropic process. And what that means is delta S is 0. You see whatever this S is right here? It's the same S here as here because the isentrope got the same S. The entropy doesn't change. The delta S is 0. So that really helps us a lot. We're just going to look up the entropy there at state 1. Go to your tables, and at 1800 kilopascals and 400 Celsius, here's the entropy. The entropy, the specific entropy at state 1, according to the table, is 7.1793. This is on table B.1.3. See, what I did was I looked up 1800 kilopascals and 400 Celsius. And I need somebody to find that and say, they found it. Can you find it? 1800 kilo? Yeah, there's an Good going. Well, here's the beautiful thing. If that's S1, we'll call this state 2S. We'll give it a name. We'll call this S, I don't know, 2S. We'll give it a goofy name there. Guess what? It's going to be the same because this is an isentrope. Same entropy. Delta S is 0. 7.17, can't read my own writing, 93. All right. We're just going to look it up at 200 kilopascals, though. Help me find 200 kilopascals. And I found it. And here's where I need some room. We don't need all this. We know that by heart. Go to 200 kilopascals. Table B.1.3. And see, we're looking for 7.1793. Well, I don't have one. 7.17. I'll tell you what they do have. We need 7.1793. Now, do I have that right? I got a bad feeling I did something wrong. Let me double check here. 1800 at 400C, and 7.1793. That's what it says. Yeah. Okay, here's what they do have at 200 kilopascals. Under the S table, we need the H's. We need the V's. Here we'll need H's, V's, and T's. There we go. Now the temperature is 120.23. And the V is point. Let me scoot that over a bit. I need some room there. I'm crowding myself here. We need a column for T, V, H, and S. And we have 7.1271. See if you can find these in your table at 200 kilopascals. We're doing water. And this is 270663. And this is 0.88573. And this is 120.23. And then the next line is 7.2795. And the H is 2768.8. I hope you can read my writing. And then the specific volume is 0.954, I think. Yeah, that's right. And the temperature is 150. We're going to interpolate. We know what this S2 is. It's 7.1793. 7.1793. What we really need is this one here. Well, we could get it. Let's get that. We only have 6 minutes. Doggone it, time goes by so fast in this class. Well, no, wait a minute. Wait a minute. No, we're here to 12:20, aren't we? Yeah, we got plenty of time. No problem. Okay, I'm gonna interpolate and get this H. I want you to do the same. Go for it. Right now, we're trying to interpolate and get this value for specific enthalpy on table B.1.3 at 200 kilopascals. So see if you can do it. Well, I wonder if you're getting what I'm getting. I'm getting 27.92. Does that even look right? Yeah, it looks right. We're going to need that. And I want the temperature too. I want to show you the temperature is going to cool off. Let's find the temperature. Here goes. I'm getting 130.4. This temperature right here, it'll be colder if you had an isentrope. Here we go. Let me doctor this up just a tad. I don't like the way this kind of curved upwards there. It's straight. It's not supposed to curve upwards like that. And this temperature here, it's colder. Whoops. There we go. It's 130.4 degrees Celsius. See, the actual turbine cools off to 150, but the isentropic turbine is colder, and it's cools off to 130.4. And we have the enthalpy. And now we can write. The work of the reversible process. Here we go. I just need the room to do it. Where am I going to find that? Hey, there's a little bit of room right here. Yeah, here's some room right here. Now what we're going to do is we're going to write the first law of thermodynamics for the isentropic process. We can write the first law for any process we want to. And we can certainly write it for this process going from here. What is that? State 1 to state 2s. We can do it. All right, here goes. Well, you know how it goes, so I won't bore you. I'll put a 0 there for the dE dt, the steady state change in total energy with respect to time. And then 0 for the adiabat minus W dot plus M dot H1 minus M dot H, we'll call it 2s, because that's what this is. That's the specific enthalpy if you had an isentrope. So if you divide through by M dot and do some algebra, you can write your little w for your reversible process as H1 minus H2s. And H1 we know. It's sitting right here, look. It's 3250.9. And H2s we just cooked up. It's 2792. So we can get the work done per mass by the reversible process. Here goes. I'm doing it. Well, I did all that and I got the work done by the reversible process to be 522 point, let's just round it off, 523 kilojoules per kilogram. Now, the work done by the actual process is 482. The work done by the reversible process is 523. So we can divide those and get the efficiency. Let's do that. Divide those for me. Guys, I did that. And you know what I got? I got a 92%. We think that the efficiency is 92%. Now, I wonder if I got an answer book that I could look that up. Let me dig around here and see. What was this, 792? I might have an answer book. Let's see what we got here, 792. Boy, Jove. Guess what the book says? The answer book says 92% is the efficiency of that turbine. Wow. Even the blind squirrel finds a nut now and then. Now, Mohammed asked for that, I think. Mohammed, were you the one that asked for that?
Yes, yes, sir.
Did you understand it?
Yes, sir. Thank you very much.
Oh, you are very welcome. Does anybody else have a comment or question for me? Comment or question for me? Well, let's do another one. We'll do another one. That was so much fun. I think we should do another one. How about you? You're supposed to say, yeah, sure, Mr. Cookie. Okay, well, I'm going to erase all that and we're going to do another one. All right. I'm going to erase all this unless you have a question. Okay, we'll say goodbye to that one. That was problem 792. And we're studying the efficiency of turbines, actually, is what we're doing. Now, that one was done with metric stuff, SI, you know, meters and all like that. Let's do one. Well, no, wait a minute. That one's also meters. I was thinking about doing one with Inglés, senor. Hang on a minute. Let me kind of shop around. Well, we did the throttle in English. You got to know how to work in English. Let's do this one. This one's in Inglés. And it's fairly short one. We might be able to get through it if we hustle. Now what this one is 7152E. E stands for Inglés. Only the way they spell Inglés is, it should be spelled with an I, right? Inglés? Oh, well. That's the same thing. It just means English. It's just that I think that's how they spell Inglés, senor. Okay, let me find it. It's 7152E. This will be fun. I found it. A steam turbine inlet. Well, let's draw the device sketch. And they want the efficiency again. Okay. It's a steam turbine. And coming in, we have 300 PSI. At 800 Fahrenheit. Going out, we have 40 PSI and 500 Fahrenheit. Well, let's look up some stuff. Go to the tables, but now go to the English tables and look up 300 PSI. I'm trying to find it here. There it is. And 800 Fahrenheit. We could write down all this stuff. It wouldn't hurt us. Let's just write it all down. Here we go. Little v1 is equal to 2.4421. I don't think we need the U's, but we will need the H's. Little h1 is 1420.99. See if you can find this stuff. And little s1 is equal to 1.7187. If you have trouble finding that, let me know. That's coming in. Now let's get the stuff going out. Find 40 PSI in the tables. If anybody has trouble, just speak up. Okay, let's write down a little v2 now. Little v2 is 14. This is pretty boring, but it's easy. This is certainly easy. Little h2 is 1284.91, and little s2 is 1.8140. Now, I was exceedingly lazy and I did not put my units on there. Shame on me. Put your units on there. See, this is cubic meters. No, wait a minute. Auga. In English, you know what? It's cubic feet per pound mass, isn't it? Let me ask one of my outstanding students. Let's see. How about my friend Nathan? Unmute and say hello, Nathan. Yeah, hey, Nathan, what's the units for specific enthalpy in English? What do I put here?
BTU per pound mass.
Yeah, he knows. He knows it's BTUs per pound mass. Good going, Nathan. Nathan, as long as I got you on the line, what's the units for specific entropy?
BTU per pounds mass Raken.
You got it, boy. Boy, Juve.
All I have to do is read.
Yeah, we could do the rest. We're doing fine. Okay. Now what? Well, what are we supposed to do? I got lost. Let me go back and look at the problem here. 7152E. I got lost. It says here, oh, they want the efficiency. All right. Well, remember how to do that. The efficiency is that eta thing, and it's equal to the actual divided by the reversible specific work. Okay, now to get those, you use the first law of thermodynamics. All right, well, let's do it. Well, the first law, you know how it goes here. I'll write it again for you. Maybe if we if we do this enough times, it'll start sinking in. What do you think? Might start sinking in. Actually, there's some other terms here, but we don't need them. They're kinetic and potential terms. This turbine is not moving. It's sitting still. It's like in a building. And it's not going up in altitude either. It's not going up. It's not going anyplace. You don't need those other terms. Isn't that nice? Now, when you plug in your numbers, this is 0 because there is no change in your total energy with respect to time. We're dealing with water, right? Now, let me put water on here. H2O, there you go. And these turbines are essentially adiabatic, so we can put a 0 there. If you go through this equation and divide through by your mass flow rate, you can get your little w. Now we're doing the first law for the actual turbine. Okay? That's what we're doing. And if you divide through by m dot, then you'll just get H1 minus H2. Hey, look at here, we got H1 and we got H2. We can get the work per mass for the actual turbine. And go ahead. I can do it. I've got a calculator. You do it. Well, I think I got the answer. I got 136.08 BTUs per pound mass. If you got that, say, uh-huh.
Uh-huh.
Yeah, there's 2 of us now. One more, uh-huh.
Uh-huh.
Yeah, there's one. Okay. Hey, we're making progress, guys. Look here. We've got the actual work per mass. If we could find the reversible work per mass, we'd have it made. Now, how are we going to do that? We're going to write the first law. We're going to write the first law of thermodynamics for the isentropic process. What that is delta S is 0. Well, now, how do we go about doing that? Well, it'll be different. We really should draw this so that you can see it. Let me do the TS diagram so you can see this. See, this is what we're trying to figure out now. Trying to figure out what the work would be if the thing was reversible. Okay, well, here comes the TS diagram. Will that show up? Yeah, that'll show up. Okay, here we go. There you go. Now our temperature is 800 Fahrenheit. Let's look back here in their English tables and see where 800 Fahrenheit is. I'm looking in the English now. Don't look in the metric. That ain't going to help him. Go back here and look in the English, senor. And you know what? The top of the vapor dome 705. if you're doing a TS diagram, (800) is up here. There it is. See, there's your (800). Okay, and 300 psi. Well, where in the heck is that? Well, kind of hard for me to draw, but I'll try. It's somewhere in here. There you go. Now there's your state 1. We've already got all this stuff for state 1. Now state 2 is at 40 psi and 500 Fahrenheit. Let's see if I can do that. Now let me see. I got to do a little thinking here. That was at this is your 300 psi. 300 psi. And what we need is a 40 psi and 500 Fahrenheit. Well, 500 is colder than 800. Let me see if I can find it here. Hang on. I'm thinking the 500 Fahrenheit is in here. There's your 500 Fahrenheit. And what we're doing is we're going from state 1 to state 2. And it's a dashed line. See I tried to draw a dashed line. I tried to draw a dashed line. There you have it. Going from 1 to 2. But see, if you went with an isentrope, if you had a reversible adiabat, it would go straight down. It would go straight down. Now, where do you stop? Well, I don't know. We're going to find out. We're going to find out. I tell you what we know. We know that S1 is 1.787. Let me write that down. S1 is 1.7187. BTUs per pound mass Rankine. We know that. If you had an isentrope, in other words, if delta S was 0, see that's what this process is going to be. If that's the case, well, I know what little s2 is. Little s2 will be 1.7187. It doesn't change any. It's an isentrope. They call that an isentrope. All right, well, we got to find where that is. Now we know state 2 is at 400 or at 40 psi. So go with me to 40 psi and help me shop around. There it is, I found it. I just need some room to operate. Let me make some room here. Now we're at 40 psi. 40 psi. I'm in the tables. I'm in table F.7.2. And what I'm looking for is a specific entropy of 1.7187. 1.7. Okay, I think I found something here. At 320, let me make a table. Temperature, specific volume, specific entropy, or no, enthalpy, sorry, specific enthalpy, specific entropy. Temperature 320. I'm just copying this stuff out of the tables. That's in Fahrenheit. We're in English, senor. This one is 11.36 cubic feet per pound mass. This one's an 1196.90. And this one is 1.7124. Now the next one down is 1.7373. Specific enthalpy is 1216.77. Specific volume is 11.996. And the temperature is 360. Now I'm going to shut up here for, oh gosh, we're running low. We'll make it though, we're going to make it. I'm going to shut up here for a couple of minutes. See, what we want is 1.7187. Look here, 1.7187. We need these numbers in this table. For one thing, it'll tell us what the new temperature will be. It'll be colder than 500. You'll see. Okay, I'm going to shut up. You got 2 minutes. Fill in the table. On your mark, get set, go. Well, I got what I think are the values after interpolation. And I'm hoping you got those. If I made a mistake, speak up. But those look pretty good. So if you draw that on here, the new temperature is going to be 330.1. It's down here someplace. .1 Fahrenheit. So your isentropic process goes from here to here. It's colder. And the pressure there should be 40. So here, let me see if I can draw that. Let me make this just a little lower. There we go. Now I'm going to draw the isobar. Here goes. This is your 40 PSI isobar. There it is. That's your 40 PSI isobar. And this one here is your 300 PSI isobar. And remember, isobars kind of go like that. We're almost done here. We got, oh gosh, we got 3 minutes left. Will we make it? Well, I don't know if I'll make it or not. I think we're going to make it because look here, we've got the value of specific enthalpy, and so this reversible work per mass is going to be that 1201.93 minus your 1420. 0.99. And the actual work, we already have it. It's equal to 136.08. Okay, divide those out and get your efficiency. And I'll look and see if I have an answer book here. This was problem 7.152E. Take 136.08 and divide by this difference here and see what you get. And I'll see what I get. Now, I think I got these backwards. I did something wrong. Now, just a minute. I did something horribly wrong. Or did I? No. These are backwards. This should be. See, that's what happens when you get into a hurry. Those go the other way. It's 1420 minus that. Go ahead and subtract it the other way. We don't have time to write it out.
Is it 62%?
Hang on a minute. I almost have it.
That's what I got.
I'm getting 62%. Now let me look at the answer book and we'll see what it says. This is 7.152E. And boy, Joe, that's what the answer book says. They said 62%. And so we conquered that one. That didn't take that long, really. But it was an English problem. You got to know how to work in English. Okay, well, it's sad, but our time together is over until we meet again on Tuesday at 11. Here's your last chance to say anything. Speak up.
Professor, I just wanted you to know, for the last couple classes, you've held the attention of a 4-year-old, my son. He's been watching your lecture. He loves.
That's hilarious. That is hilarious. Hey, he might decide to go into engineering. You know what?
You never.
What's his name? May I ask?
John.
John? Or Sean? I didn't quite hear you.
It's John. It's John. I don't know if you
John.
can see him. Want to say
Yeah.
hi?
Hey, John, I'm so glad you like my thermo lectures. I'm so glad. Hey, they're on YouTube. You can watch more of my lectures if you want, John. Just go to YouTube. Your dad knows how to do it. Okay, guys, it's been fun, but I'm gonna
Thank you.
click. I'm gonna click this red button. We'll see you next time. Okay. Adios, muchachos.